Welcome to Section 1, Lesson 3. Today we look at absolute value, written as a number wrapped in two vertical bars. It is one of the simplest pieces of algebra notation and also one of the most quietly useful. Absolute value shows up in distance formulas, in error tolerances, in solving equations with multiple cases, and in nearly every physics formula that asks how big something is regardless of direction. First idea on the board: absolute value is always positive or zero. It is never negative. The reason is that absolute value measures a distance, and a distance cannot be negative. The bars do not change the magnitude of the number, they only strip away the sign and leave you with how far that number sits from zero on the number line. Second idea: the absolute value of a minus b gives you the distance between two numbers on the line. It does not matter whether you write it as the absolute value of a minus b or the absolute value of b minus a. Both give the same answer because distance does not care about direction. This will become the standard way to compute distance in every coordinate system you ever meet, in 2 dimensions, 3 dimensions, and beyond. An equation like the absolute value of x equals 5 has two correct answers, not one. Both x equals plus 5 and x equals minus 5 satisfy it, because both are exactly 5 units away from 0. This two-solution property is the surprise that catches most students the first time they meet absolute value equations, and we will work through it carefully later in this lesson. Here is the number line with tick marks at every integer from -5 to +5. 0 sits in the exact middle, and the line stretches off in both directions with arrows. We are going to use this picture to build the meaning of absolute value layer by layer by reading off distances directly from the line itself. Take the number +3. A blue dot lands on the tick at 3. Now look at the cyan double arrow that runs above the axis from 0 to 3. That arrow has a length of 3 units. So the absolute value of 3, written as the number 3 between two vertical bars, equals 3. The label appears above the arrow as the absolute value of 3 equals 3. The bars did nothing visible to the number because 3 was already positive. Now take the number -4. A pink dot lands on the tick at -4. Look at the pink double arrow that runs below the axis from 0 to -4. That arrow has a length of 4 units, even though we traveled to the left. So the absolute value of -4 equals 4. The pink label below confirms it. The bar stripped away the negative sign and gave us the magnitude of the distance from 0, which is always positive. And the special case: take the number 0 itself. A green dot lands at 0. There is no distance to travel because the number is already at 0. So the absolute value of 0 equals 0. 0 is the only number whose absolute value equals itself unchanged. Every other number has its sign stripped away by the bars. Now we lift the picture and write the formal definition. The absolute value of x equals x itself when x is greater than or equal to 0, and equals -x when x is less than 0. Two cases joined together with a brace into one definition. The negative case looks strange because of the minus sign, but read it carefully. If x is negative, then -x is positive, so the answer is still positive. The minus sign in the second case is doing the sign flip that makes the result non-negative, exactly as the geometric picture demanded. The single most important takeaway from this scene: absolute value is a distance, so it is always non-negative. Whether the input is positive, negative, or 0, the absolute value comes out as 0 or larger. This non-negative property drives every other rule about absolute value, including the two-solution property, when we solve absolute value equations later in this lesson. Here is our first worked example. Two blue dots sit on the number line, one labeled a equals -3 on the left, the other labeled b equals 5 on the right. Our job is to compute the distance between them using absolute value notation, and to verify that we get the same answer no matter which direction we measure in. Step 1. Plug a equals -3 and b equals 5 into the formula absolute value of a minus b. We get the absolute value of -3 minus 5. Notice how the -3 goes inside the bars exactly as written, with parentheses to keep it visually separate from the minus sign that connects a and b. The label on the left says we are substituting the values of a and b into the distance formula. Step 2. Simplify what is inside the bars. -3 minus 5 equals -8, so the expression becomes the absolute value of -8. The bars are still there because we have not taken absolute value yet. We have only simplified the arithmetic inside. Step 3. Take the absolute value. The absolute value of -8 equals 8, because 8 is the distance from 0 to -8 on the number line. The bars come off and the negative sign disappears, leaving us with 8. So the distance between -3 and 5 on the number line equals 8 units. Step 4. Now check that we get the same answer in the reverse order. Compute the absolute value of b minus a, which is the absolute value of 5 minus -3. 5 minus -3 is the same as 5 plus 3, which equals 8. So the absolute value of 8 equals 8. Same final answer as expected. Distance is symmetric, the order does not matter. So the final answer is 8. Two takeaways from this example. First, the absolute value bars are essential because without them we would have gotten -8 in the first version and +8 in the second version, two different answers. Second, the bars hide the direction, so the answer always represents how far apart the 2 points are, not which one is to the left or right of the other. Here is the second worked example. The equation at the top reads the absolute value of x equals 5. Below the equation we have a fresh number line with a dot at 0 in the middle. The question is, which values of x make this equation true? Most students start by guessing x equals 5 and stopping there. We are going to see why there is actually a second answer hiding on the negative side of the line. Reframe the equation as a distance question. The absolute value of x equals 5 is the same as asking which numbers on the line sit exactly 5 units away from 0. Once we phrase it this way, the answer becomes a geometry problem instead of an algebra problem, and the picture does most of the work for us. First answer. Move 5 units to the right of 0 and we land on +5. A cyan dot appears at the tick for 5 and a cyan double arrow shows the 5-unit jump from 0. The label below says x equals +5, which is one solution to the equation. So far this matches the obvious guess most students make at first glance. Second answer. Move 5 units to the left of 0 and we land on -5. A pink dot appears at -5 and a pink double arrow shows the 5-unit jump from 0 in the leftward direction. The label below says x equals -5, which is the second solution. Both points are exactly 5 units from 0, so both satisfy the original equation. So the full answer is x equals +5 or x equals -5. The green line in the center collects both solutions into a single statement using the word or because either value satisfies the equation. This two-solution pattern is unique to absolute value equations and is the key thing that makes them different from regular linear equations. Here is the general value of x equals n, means x equals plus or minus n, written with the plus or minus symbol, valid whenever n is greater than 0. This single rule covers every absolute value equation of the simplest form and is the starting point for solving more complex ones in section 3 of the course. Two corner cases to remember. If n equals 0, the equation absolute value of x equals 0 has only one solution, x equals 0, because 0 is the only number that is exactly 0 distance from itself. If n is negative, for example absolute value of x equals -2, there is no real solution at all, because absolute value can never be negative. Always check the sign of n before reaching for the plus or minus rule. Three mistakes that catch almost every algebra student when they first work with absolute value. Each one comes from a small mismatch between the algebra notation and the underlying geometric meaning of distance. We will go through each one in turn with the right way to think about it. First mistake. A student writes the absolute value of a minus b equals the absolute value of a minus the absolute value of b. That equation looks plausible because absolute value bars resemble parentheses, but it is wrong. Absolute value does not distribute over subtraction or addition the way multiplication does. The right approach is always to compute the value inside the bars first, then take the absolute value of the single result. Never split the bars across an operation. Second mistake. A student is given the equation absolute value of x equals minus 3 and writes x equals minus 3 as the answer. That is wrong because absolute value can never be negative. The bars always produce a non-negative result, so an equation like absolute value of x equals a negative number has no real solution at all. The student should write no real solution as the answer and move on. Third mistake. A student sees the absolute value of x and thinks they can drop the bars and replace it with x. That is only safe when you already know that x is non-negative. If x might be negative, the bars become essential because they flip the sign. The general rule is only drop the bars after you have explicitly checked the sign of the expression inside, or after you have split the problem into separate cases for positive and negative inputs. Absolute value is one of the most quietly useful pieces of notation in applied mathematics. Anywhere the question is about how big a difference is, regardless of direction, you will find absolute value bars in the formula. Here are 4 real-world places where absolute value does the work without being mentioned by name. On a thermostat, the controller measures the deviation of the room temperature from the set point. If the set point is 72 degrees and the actual room reading is 68 degrees, the deviation is the absolute value of 68 minus 72, which equals 4 degrees. If the room is at 76 degrees instead, the deviation is the absolute value of 76 minus 72, also 4 degrees. The absolute value lets the thermostat treat both cases the same way because 4 degrees too cold and 4 degrees too hot are both 4 degrees off target. On a GPS receiver, the device estimates how accurate its current position fix is by comparing the measured location to a known reference. The error magnitude is the absolute value of the measured position minus the true position in meters. The absolute value strips out the direction so the user just sees a single positive accuracy figure, like plus or minus 3 meters. Without absolute value, the error could be negative depending on which direction you measured, which would be confusing. On a stock chart, the daily move is often reported as an absolute change. If a stock closed at $100 yesterday and $104 today, the move is the absolute value of 104 minus 100, which equals $4. If the stock instead closed at $96 today, the move is the absolute value of 96 minus 100, which is also $4. The absolute value lets traders compare the size of the move regardless of whether the price went up or down. In engineering, every manufactured part has a specification and a tolerance. A tolerance check asks whether the absolute value of the measurement minus the specification is less than or equal to some small allowed error called epsilon. If the part comes out within plus or minus epsilon of the spec, it passes. Without absolute value, the engineer would need 2 separate checks for too high and too low. With absolute value, one inequality covers both. 3 things to take with you from this lesson before we move on to the next one. Each one will come back many times in later sections, especially when we get to inequalities and to coordinate geometry, where distance becomes a central quantity. First, absolute value, written as a number wrapped in 2 vertical bars, is the distance from that number to 0 on the number line. The result is always 0 or a positive number, never a negative number. This is the geometric meaning that drives every algebra rule about absolute value. Second, the absolute value of a minus b gives you the distance between any two numbers on the number line. The order does not matter, so the absolute value of a minus b equals the absolute value of b minus a. This formula is the building block for the distance formula in 2 dimensions and 3 dimensions later in the course. Third, an equation like the absolute value of x equals n has 2 solutions, plus n and minus n. Whenever n is greater than 0, it has one solution 0 when n equals 0. And it has no real solution at all when n is negative, because absolute value can never come out negative. Coming up next, the lesson called Exponent Rules Part 1, where we look at what x squared and x to the fifth really mean. See you there.